Hey guys, and welcome to GP Academia. Electrical technology has provided a means to acquire biosignals important in modern clinical and diagnostic equipment used in medicine and biological researches. In this short lecture video, I will give a general discussion of various technologies that we utilize in the life sciences. Let's start. This is the outline of this lecture. Given that our senses as humans are limited, there is a need to develop instruments that can aid us to detect signals outside our capabilities. Sound waves above, let's say, 20 kHz cannot be detected by our ears. We also have a limited visible range in terms of electromagnetic wavelength. We can only see electromagnetic waves with wavelength of about 400 nanometers and 700 nanometers. We cannot sense small magnitudes of electric field. Through the development of electrical technology, we were able to detect very small signals that improves our research capabilities, aids our senses, and improves the accuracy of medical diagnosis and treatment. In the picture, this one, we have a biological sample acquired using confocal microscope. Confocal microscope is an instrument that provides a high-resolution image with all the areas in focus throughout its field of view, even for a sample having dents or damages on the surfaces. They enable the non-contact, non-destructive measurement of three-dimensional shapes. So I have here the general flow chart used to detect signals for life sciences applications. The starting point is a phenomenon or a signal that we want to observe but cannot be detected naturally by our senses. It can be an electrochemical activity of a biological sample, frequency of a sound produced by an animal, let's say, or the light emitted by a fluorescent dye from a biological sample. In my picture, this is made from a molecular probes demo slide of bovine pulmonary artery endothelial cells stained with fluorescent dye used in confocal fluorescent microscopy. The nucleus is in blue and the microtubules is in green. Next step is the conversion to electrical signal. This one. For light, it can be converted into electrical signal or current using a photomultiplier tube shown here, the picture above. A photomultiplier tube or PMT is used for light detection of very weak signals. It is a photoemissive device in which the absorption of a photon or light results in the emission of an electron. Third, we need to amplify the signal because it is commonly too weak to be displayed in the output of our instrument. Here I have a picture of an instrumentation amplifier. It is a differential op-amp circuit providing high input impedance with ease of gain adjustment through the variation of a resistor commonly used in biomedical instrumentation. Signal processing can be done to remove noise and extract relevant signals before displaying it to the output. Then, the final signal will be displayed. For fast signal, a device called an oscilloscope is commonly used. Many of our modern diagnostic equipment utilize electrical technology. First picture here is a device used in gastroenterology. And this is a 24-hour esophageal pH metry. This is a test to confirm the presence of reflux and mainly to assess the severity of the reflux. The test results can be used to effectively decide with regards to the medical treatment and if what endoscopic or surgical methods are needed. Next, the picture on the right is a bispectral index or BIS and is one of the several technologies used to monitor the depth of the anesthesia. This is an electroencephalogram derived multivariate method, and we can correlate this signal to both loss of consciousness and awakening from anesthesia. Other applications include hearing aids and cochlear implant. The human heart can be considered as a large muscle whose beating is simply muscular contraction. Therefore, contractions of the heart generates an electrical potential that can be measured. The measurement of the potential produced by the cardiac muscle is called electrocardiology. For the cardiovascular system to function correctly, both the atria, so the upper part of the heart, and the ventricles, the lower part of the heart, must function in proper time relationship. The heart has a special system. First, to generate rhythmical electrical impulses to cause contraction of the heart muscle. And second, to conduct rapidly these electrical impulses throughout the heart. The atria contracts about 1/6 of a second before of the ventricular contraction to allow filling of the ventricles before it pumps the blood through the lungs and the peripheral circulation. I will not discuss here the detailed mechanism of this conductive system. I will just describe the flow of the impulse. So the picture here shows this specialized conduction system of the heart that controls the cardiac contraction. We have here first the sinoatrial or the SA node, so this one, in which the normal rhythmical impulse is generated. It has a resting membrane potential of about -55 to -60 millivolts compared to the ventricular muscle fiber with about -85 to 90 or -90 millivolts. Then we have this internodal pathway to or that conduct the impulse from the SA node to the AV node or to the atrioventricular node. So this one, the AV node. The AV node is where the impulse from the atria is delayed before passing into the ventricles. AV bundle here, so this one, the AV bundle, is where it conducts the impulse from the atria into the ventricles. Last, we have the left and the right bundles of or bundle branches of Purkinje fibers, which conduct the cardiac impulse to the rest of the parts of the ventricle. So this one. Other parts of the heart exhibit intrinsic rhythmical excitation, similar with the SA node. The SA node, however, normally controls the beat of the heart because its rate of rhythmical discharge is faster than any other parts of the heart. That's why it is said to be virtually the pacemaker of a normal heart. When the cardiac impulse passes through the heart, electrical current is also distributed from the heart into the adjacent tissues around the heart. A small portion of the current spreads also to the surface of the body. These electrical potentials generated can be recorded, and this is called electrocardiogram. In this picture, we have a normal electrocardiogram composed of P wave, the QRS complex, T wave, and sometimes we also see this U wave. The P wave is generated due to the electrical potentials created by atrial depolarization before the atrial contraction starts. The voltage of the P wave is between 0.1 to 0.3 millivolts. Then the QRS complex is caused by potentials created due to the ventricle depolarization before contraction. This depolarization spreads through the ventricles. The voltage of the QRS complex is commonly between 1 to 1.5 millivolts from the top of the R wave to the bottom of the S wave. Thus, a P wave and the QRS complex are depolarization waves. Next, we have the T wave, and this is due to the potentials created as ventricles recover from depolarization. It happens commonly if or in ventricular muscle about 0.25 to 0.35 seconds after depolarization. The T wave is called repolarization wave. It has a voltage between 0.2 and 0.3 millivolts. Last, we have the U wave. The U wave here comes after the T wave. It may not always be observable due to its small size. The exact source of this is unclear, but the common theory is that this represents repolarization of the Purkinje fibers. ECG recordings are made with correct calibration lines on the recording paper, such as this. The horizontal axis represents time, and the vertical axis represents the voltage. The standard values on this grid are shown here. So a small box, so this one, such as this, a small box is 1 millimeter by 1 millimeter and represents 0.1 millivolts for the vertical, and the horizontal that represents 0.04 seconds. A large box such as this is, this one is 5 millimeter by 5 millimeter and represents 0.5 millivolts for the vertical, and for the horizontal that's 0.20 seconds. Rate of the heartbeat can also be determined from this easily, because the heart rate is the reciprocal of the time interval between two successive heartbeats. Okay, so I have this drawing. My drawing at the left shows the ventricular muscle within the chest. The apex is the most inferior, anterior, and lateral part of the heart and formed by the left ventricle, while the base of the heart is the posterior part and formed by both the atria. The heart is surrounded by a conductive medium that enables us to measure biopotentials at the body surface. When one part of the ventricles depolarize, it becomes electronegative relative to the remaining parts as shown here. Electrical current flows from the depolarized area, this one, to the polarized area. So this yellow curves shows the current flows. Note that the impulse arrives first in the septum of the ventricle before it spreads to the inside surface of the ventricles. So that's why we have here first the negative sign. Thus, we have this electropositivity on the outer walls of the ventricles. Therefore, the average current flows with negativity at the base of the heart and the positivity toward the apex. This is observable in the voltmeter with a positive deflection attached at points L, so this one, first point, or the left side of the body, and R, or the right side of the body. On my drawing at the right, this one, it shows the common arrangement of electrodes in standard electrographic leads. Einthoven's triangle is superimposed on the chest area as well. This drawing also shows the bipolar limb leads, meaning recording from two electrodes. That's why it's called bipolar. So here, the right arm is assigned with negative 0.2 millivolts relative to the average body's potential, while the left, so this one, left arm, has positive 0.3 millivolts. And the left leg, this one, has positive 1 millivolts. All the leads 1, 2, 3 records positive values. According to Einthoven's law, if the electrical potentials at or of any two of the bipolar limb leads are known at an instant, the third one can be calculated by summing the first two, taking note of the sign of the triangle. So this one, this refers to the Einthoven's triangle. If we try to add, let's say, the lead 1 and lead 2, this 2, the potential difference, we will get this value for lead 2. Leads are electrode setups which measure the difference in electrical potential between either first two different points on the body, and this is called the bipolar leads. Second, one point on the body and a virtual reference point with zero electrical potential located in the center of the heart. So that's unipolar leads. Each lead gives a slightly different representation of the electrical activity of the heart. For standard ECG, we have 12 leads. First, 3 standard limb leads that includes L1, L2, and L3. This is used to diagnose, let's say, cardiac myopathies or cardiac arrhythmias. We have also 3 augmented limb leads in recording augmented unipolar lead. 2 of the limbs are connected through electrical resistance and to the electrical terminal, and the third limb is connected to the positive terminal. When the positive terminal is on the right arm, so we have AVR lead. On the left arm, we have the AVL lead, and on the left leg, we have the AVF lead. We also have 6 precordial leads. These are chest leads that includes 6 standard chest leads from the anterior chest wall. That includes V1, V2, V3, V4, V5, and V6. Next, we have Electroencephalograph, or EEG. It measures potential along the surface of the scalp. This instrument occurs collective neural activity in the brain, and EEG represents the measurement of the electrical signals associated with the function of the brain. Again, the electrodes are attached at the scalp, and the position depends on the goal of the EEG. The potential difference between the electrodes and a certain reference electrode commonly placed to the ear are being measured. The typical values of this or amplitudes are in the range of 30 to 50 microvolts. Thus, it is susceptible to electrical noise because this is very small. The intensity of the brain waves from the scalp is mainly dependent on the numbers of neurons and fibers firing impulse in synchrony with one another. Brain signals are grouped based on frequency and can be divided into alpha, beta, theta, and delta waves. So I have here this table that shows the prominent signals that mainly depends on the age and activity of the patient. Next, we have electromyography or electromyogram, EMG. Electromyography measures muscle response or electrical activity in response to a nerve's stimulation of the muscle. The electrical activity from the motor nerves triggers muscle contraction, and the speed of the signal transmission determines the response time. EMG mainly measures the speed of muscle response and allows to test the muscle function. This electrical activity is measured by planting these electrodes directly under the skin into the muscle fiber. Electrodes collects the electrical signal, which is amplified and displayed as a function of time. You can generally use a needle or plate electrodes for this instrument, and the response signal can be detected after some latency time. The response signal can be detected using 2 or 3 electrodes as well. So we have this delay, the measurement distance, and the speed of the signal. And I have this table for the physiological effects of electricity. For threshold current level, a tingling sensation or fuzzy feeling will be perceived. The pain level may feel like a sharp bite if you encounter this amount of current, and let go current level, this one, may result in nerve and muscle strong stimulation that may result in pain or fatigue. Paralysis current level, the muscle may lose their ability to relax, resulting in respiratory paralysis. Fibrillation level is when heart goes in fibrillation or the unsynchronized heart contraction that may result to death. Last, we have defibrillation level, and this is the delivery of electrical energy to the fibrillating heart. It can resynchronize all the cardiac muscle. Biological processes are controlled by a certain requirement. Examples are the thermoregulation or the control of light intensity reaching the retina. This type of system is also present in electrical systems. This measured quantity or the parameter is being controlled by comparing its value to a given reference value, or this one. Comparator will control the measured quantity based on its difference relative to this reference value. Next, we have a feedback system, as shown here. It uses as input the total or partial output of the system. Feedback systems are used to control and regulate processes. It can oppose or augment the input. This is called negative and positive feedback. I will not derive it here, but depending on the sign of the beta, here if the system has a negative or positive feedback. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, GT Academia. See you in the next video.